So we are on page 309 in our notes packet, and we should be following along and taking notes. This is an extremely important FRQ topic. I can almost guarantee you that this topic will be at least an entire FRQ question on our AP exam, and it will likely be even a lot more than that. So what we're going to basically kind of look at is that the derivative of some amount of something, right? The derivative of an amount is the rate at which that amount is changing. Okay? So, for example, if water is being drained from a swimming pool and we have R of T as the amount of water in cubic feet, then R prime of T would be the rate that the amount of water is changing, right? So, what units would we have R prime of T in that case? Well, if we kind of look back up here, we had R of T in cubic feet, right? That was R of T. So if we're doing this, then this would be cubic feet per hour, right? Because we were using hours, right? So as we take a derivative, we add on a per time. Now, this is kind of our new part, is that our integral of a rate is the amount of change. Okay, it's the amount of change, or the net change, but amount of change is good. So in this case, right, we want to kind of think about what would the integral of R prime of T dt represent. Well, FTC tells us that the integral of any derivative is big R of B minus big R of A. So this would be the change, the amount of change of the water in cubic feet. That's what R of T is from T equals A to T equals B. And this is kind of our big key for today. So jumping into an example, just so we can kind of see this in action. If we were given a table representing the velocity of a particle, and we want to approximate the value of the integral from 0 to 30 using a midpoint Riemann sum, explain what that means. And this is a little bit review from yesterday as well. So midpoint sum, 0 to 10, 10 to 20, 20 to 30. Those are all 10. So 10 times the middle, 1.6, plus 10 times the middle is 3.1, plus 10 times the middle is again 1.6. And so you can go ahead and type that into a calculator. I'm going to just add in 0 to 30, v of t dt approximately. And when you type that into a calculator, you're going to get 63 feet. So now, using correct units, explain what this means. That's what I kind of want to focus on, is the integral from 0 to 30 of v of t dt is we're always going to say the amount of change, or the change in the amount. So you could easily just say the amount of change of the position of the particle in feet from t equals 0 to t equals 30 minutes. Now, honestly, reading that back, the amount of change kind of sounds silly, so I'm going to just say the change of the position, but you can always use amount of if you want. So what is the value of the integral from 5 to 25 of a of t dt? So for this one, the integral from 5 to 25, this is a of t dt. We do not have a of t in our table, but this is, and when they kind of say what is the value of this, it's not a Riemann sum. That's a hint that it's always going to be FTC. So this is v of 25 minus v of 5. You just look back up at your table. V of 25 is 1.6 minus v of 5 is also 1.6, so we get 0 feet per minute. Okay. And what this represents, the integral from 5 to 25 of a of t dt, represents, and again, you can say amount of change of velocity, or you can just say change of velocity. So it represents the change of velocity. What are the units of velocity? They're feet per minute, so in feet per minute, from t equals 5 to t equals 25 minutes. Okay, so that was a little bit of review from yesterday. Now we're going to jump into totally different problems that have nothing to do with particle motion. So we have a temperature of water in a tub, and they do tell us it's increasing. That may come into play. A lot of times that comes into play with things like our approximations, right? That's concave up actually. But our Riemann sums, right? Like, increasing would be below for a left Riemann sum, increasing would be above for a right-hand sum. So that's when we see words like increasing or concave up on these table questions, a lot of times we're thinking about that. And anyways, they give us W, and they're telling us that W of t is measured in degrees Fahrenheit, right? That was the temperature of the water. So W of t is just the temperature of the water. So using the data in the table, figure out or estimate what W prime of 12 is. Whenever we're estimating a derivative, that's always y2 minus y1 over x2 minus x1, f of b minus f of a over b minus a. So this is W of 15 minus W of 9 over 15 minus 9. You can write it that way, or you can write it as 67.9 minus 61.8 over 15 minus 9. You guys have a calculator, you can just use your calculator. And when you type this into your calculator, I'm going to actually change these to approximately, we get 1.017. And the units are going to change from degrees Fahrenheit to degrees Fahrenheit per minute because we're approximating a derivative, so we're going to add on that per time. Okay, and then what we'll say is that W prime of 12 is the change in temperature in degrees Fahrenheit per minute at time equals 12 minutes. You'd also say the temperature is increasing. Another way to say this is you'd say W prime of 12 equals 1.017 degrees Fahrenheit per minute is the rate the temperature of the tub is increasing, and the reason the temperature of the tub is increasing is because it's positive at t equals 12 minutes. I personally like the first way better, but that is another way to say it. All right, use the data to evaluate the integral from 0 to 20 of W prime of dt. And again, they say evaluate. They're not giving us a Riemann sum. That's a hint that this is FTC. So the integral from 0 to 20 of W prime of t dt, right? If I look at my table, it's not W prime, it's W. So I need to get this back to W of 20 minus W of 0. That's FTC. So this is going to be W of 20 is 71 minus 55, which is 16. And when I take an integral, W prime would be degrees Fahrenheit per minute. So I would chop off that per minute. It's back to degrees Fahrenheit. Right? Also, it's the same units as W, which is degrees Fahrenheit. So using correct units, explain what this means. So the integral from 0 to 20 of W prime of t dt is the amount of change of the temperature of water in the tub in degrees Fahrenheit from, or between, you could also say between, t equals 0 to t equals 20 minutes. So that's a big thing. We're going to just do it over and over and over again. And you're kind of just always looking for the integral, then the amount of change, then of what it is, then units, then from time. So it's always just that pattern. All right, from 20 to 25, from time 20 to 25, the function w that models the water temperature has a first derivative given by the function w prime of t equals 0.4 rad t cosine of 0.006 t. This is a very common, part C or part D on an FRQ, and it's pretty tricky. But basically what this is saying is that, from time 0 to 20, we were given these temperatures on the table. Then after time 20, so like starting after time 20, now we can start using this equation. But this is specifically for w prime of t. So we got to be careful here. So we want to know what is the temperature of the water. Now, this is kind of the meat of what we're doing today, right? If we're given, I'm going to kind of write this down here. If we're given w prime of t, how do we go back to w of t, right? Well, if we want to go back to w of t, we need to take an integral, right? And so what FTC is going to basically tell us is that some w prime at some new time b equals w prime at our initial condition plus the integral from a to b of, this should be w, there we go, w prime of t dt, right? So this would be the, the w of b is equal to the w of a plus the integral of w prime of t dt, right? And that's basically just saying that, some new temperature equals our initial temperature plus, and this is the integral of the rate, and the integral of the rate is the change in the temperature, and that should make perfect sense, right? The new temperature is going to be whatever the starting temperature is plus however much it changed by. So what we want to find out is we want to find out what is the temperature at time 25. So that's going to be like, w at 25, that's going to be like our w of b, right? So we want to know temperature at 25 will equal to, now we don't want to use 0, we want to use 20 because this equation is only working from 20 to 25. So we're going to say w of 20, and we do know that because in the table it gives us w of 20 is 71. So that plus the integral from 20 to 25 of 0.4 radical t cosine of 0.06 t dt. And you're going to just type this into your calculator. And for w of 20, you're going to type in 71. If you want to write in 71 here instead, you can. All right? But I'm not going to. I'm going to just use my calculator because it's quicker. All right, and so we type that in. We get 73.0432. And we will write that down. And actually, to be honest, we didn't even have to write this. We could have just written w prime of t. But I already did, so we're good. So we get 73.0432, and our answer is in degrees Fahrenheit. So let's look at another one of these. We have a pan of biscuits, and they're removed from an oven at some time 0, and the temperature at that time is 100 degrees Celsius. So what I'm going to kind of write out here is, and they're giving us b prime as our rate, so that means b, like just big B, would be the temperature. So I'm going to write that as b of 0 equals 100. That's our initial condition they're giving us. So now, instead of giving us a table or something else, they're giving us a formula, and specifically this is the formula for the rate. So they're giving us the rate at which the temperature of the biscuits is changing is b prime. So again, this is coming way back up to here, right? If we are given the rate, if we take the integral, that's going to get us back to the amount, right? And so the biggest part of this whole notes, I want you to kind of come back up here to the first page, right? And that was this guy here. But I want us to just add something in here. Just add wherever you have room. I want you to kind of add in the amount, right? And you can do amount like that at, sometime b is equal to the amount at sometime a plus the integral from a to b of the rate of t dt. And if you want to write the word rate, you can, or if you want to just write r, you can. Right? And so that's our formula. right? The amount at b equals the amount of a plus the integral from a to b of the rate of t dt. So that's the big concept. So we want to first it just says find the value of b prime of 3 using correct units. This is super easy, right? B prime of 3, we have a formula for b. You're literally going to just type this into your calculator. You can use the @ button. It's super easy. So I will show that, but you know, you're just typing this line in. The @ right, that @ symbol right here, that @ times 3, remember, is control equals. So don't really need to show any work at all. You're just going to write b prime of 3 equals -8.2364. They know you're using a calculator, and this will be in degrees Celsius per minute, right? Because it's the rate. And it says explain what this means. So what this means is that the temperature of the biscuits are decreasing by 8.263 degrees Celsius per minute. But if you don't want to use the word decreasing, you can just say they're changing, right? So we just say b prime of 3 is the rate of change, right? Anytime I'm doing a derivative instead of amount, right, it's the rate of change. So integral is amount of change, derivative is rate of change. So it's the rate of change of the temperature of the biscuits. Same kind of formula or sentence starter structure, whatever you want to call it, in degrees Celsius per minute. And then this time it's at time equals 3 minutes. All right, sketch a graph of b prime of t on the table below. You do have a calculator, you could use this. This is back to Math 3, Accelerated Math 3. This is an e, so it's an exponential. It's negative, and the double negative is when I had negative in front, negative before. That pattern was like this. All right, if you don't know that, it's not a big deal. All right, I'd rather you just, for this one, use your graphing calculator if you want to. Now, it says explain in the context of this problem why that graph makes sense. Well, the reason this makes sense is that the rate is basically always going to be approaching 0, right? And so the temperature of the biscuits should be decreasing, right? The temperature of the biscuits should be decreasing because they're going to start off at 100 degrees and they're going to cool down. So that's why b prime is always negative. And eventually the temperature is going to level off to some kind of a room temperature, which is why this is going to have a horizontal asymptote, because eventually b prime should approach 0, which means the biscuits are no longer changing. So you can kind of explain something like that, right? Is b prime of t is always less than 0 because the temperature of the biscuits is decreasing, right? They're cooling down. And you can also maybe mention that b prime of t approaches 0 as time approaches infinity, right? Because the temperature of the biscuits should approach room temperature. Something like that. All right, at time t equals 0, what is the temperature of the biscuits? This is our big question. This is the one we have to nail. So we want to know what is b of 10, right? So b of 10 will equal to b of whatever our initial condition is. I believe they gave us 0, right? Yeah, b of 0 was 100. And then plus the integral from 0 to 100, right? You're not always going to use 0. You're going to use whatever initial condition they give you. Most of the time it is 0. And then I'm going to just write b prime of t dt. You could write out all of that negative 13.84, but I'm going to just write b prime, and I'm going to save the writing it out for my calculator. Then I just write b of 10 equals, and then I use my calculator to get the answer. And as a reminder, when you're typing this in, you can go up here and highlight this and Control C and Control V to save yourself from having to type it one more time. You get 34.18. And the units for that will be degrees Celsius. Right? So that's really the big idea there, right? Is the new temperature, or the new amount, is equal to the original amount plus the integral of whatever our rate is. So one more like this. We have a cylindrical can, radius 10 millimeters, is used to measure rainfall in Stormville. Now, let's kind of be careful about that. If I have a cylindrical can with a radius of 10 meters, that R equals 10 is never going to change. That's a constant. We want to make sure we remember that. Right, during the first 60 days, during the first 5 days of a 60-day period, 3 millimeters of rain has been collected. The height of the water can be modeled by the function s, where s of t is measured in millimeters and time is measured in days, between 5 and 60. So they're basically telling us the first 5 days, 3 millimeters of rain has been collected, or the height is 3 millimeters. So we basically know that s of 5 is equal to 3. That's our starting point. Okay? And then they give us a rate of the height. So they're giving us a rate again, which is s prime, and that's only for between 5 and 60. So first they say find the value of the integral from 10 to 15 of s prime of t dt, and then explain what that means. So let's do that first. Integral from 10 to 15 of s prime of t dt. You don't have to write it all out. You can do that on your calculator. And actually this is an equals. This is not an approximately. So we're going to just type that into our calculator. All right, so we write that out and we get 11.159. All right, and that will be back into millimeters, right? So the S prime is going to be in millimeters per day. This will just be in regular old millimeters. And so then what that represents is the integral from 0 to 15 of s prime of t dt is the amount of change. I always like that when I'm doing these. So the amount of change of, and then let's just kind of go back up here, the height of the water, and then we're going to say in the units, millimeters, from t equals, oh, this was a 10 to t equals 15 days. And then at the end of the 60-day period, what is the volume of water in the can? Now, to get volume, this is kind of a two-step process. First, we need to get the height. So let's first get the height. So we want S at 60. That's going to be S at 5 plus the integral from 5 to 60 of S prime of t dt. So on our calculator, what that will look like is coming back up here, and then S of 5 was 3, so I'm going to do 3 plus, I'm going to just grab this whole integral, and then just change my endpoints from 5 to 60. Alright, that's the best way to do this. And then we get 166.56. Alright, so we're going to go ahead and write that down. So we had 166.565. I forgot the last. 565. Oh, 5649. Right, 5649. Right, and that's in millimeters. Now, in order to get volume, well, it's a cylinder, so volume is going to be pi r squared h. So our volume at 60 will be pi. Now, we said r at the beginning. We kind of talked about that radius of 10 as a constant. So pi times 10 squared times that 166.5649. You can type that into a calculator. I didn't. You can do that, and it'll be in millimeters cubed. All right, the rate at which people enter an auditorium. This is a huge common FRQ question. Is people coming in and sometimes even people coming out. So we'll get there later. Right now, it's just people coming in. So we have R of t. We're given an equation. and they say RFT is measured in people per hour. VIP tickets were sold to 100 people who already are in the auditorium at time 0. And the doors close and the concert begins at time 2. So if all of the VIP ticket holders are staying, how many people are there when it begins? So we want to know RFT is the rate, right? So if RFT is the rate, they do this, sometimes it's not R prime, right? But it kind of is, you know, a derivative, right? RFT is a rate. We got to make sure we realize that RFT is a rate. So that's why I like to have this like amount at time B is equal to the amount at time A plus the integral from A to B of the rate of T dt, right? This is our big equation. So if they give us an RFT and they just call it RFT, it doesn't matter that it doesn't have a prime, it's still a rate. So the amount at time 2 is equal to the amount at time 0 plus the integral from 0 to 2 of RFT dt. And we've done this a bunch of times now. You're just going to head over to your calculator and type all of that in. Okay, and so that should look like this. 100 was my initial plus that integral of the rate, and we get 1080, right? And so our units in this case are people. So this would be, there are 1,080 people in the auditorium. All right, so for our homework, we're gonna have just, you know, kind of a bunch of these, and you're gonna go through it the best you can. And, you know, we have a rate, we're gonna do all these different problems. The one thing that I do wanna watch out for is we still haven't actually covered this. So actually we can just kind of cross out 3. Let's just do that. And then I think 6 is a little bit interesting. It says after time 7, sand is not used anymore. So the rate isn't there, but sand is still being added, right? And so in this question here, it's a little bit different. It's a little bit harder than the one that we did. And so I want to kind of talk about this is we have at time 0, there are 120 pounds of sand. That's going to be, you know, the initial amount. So basically like our amount at time 0 is 120. Now sand is being added to the tank. This is going to be a rate in. And then sand is being used. That's going to be a rate out. And so this is actually really common. And so I want you to kind of come back up here and go back to your notes. And this is super important. So we have this, you know, amount here, but what I want you to kind of even make this better, and we can put this up here. This is probably like the biggest formula for this, is that the amount at time B is equal to the amount at time A plus the integral from A to B of the rate in minus the integral from A to B of the rate out. Right? And so a lot of times they have both a rate in and a rate out. And so this is a very important concept to realize. So basically what that's saying is that our new amount is equal to the starting amount plus the integral of the rate in would be how much we add minus the integral of the rate out would mean how much we subtract or we use. So that's a huge formula. And that's what you're going to basically do here. And so we're going to have 2 rates, right? We have a rate in and a rate out. All right? And so then after time 7, they're basically saying that we're not having a rate out anymore, but we're continuing to have a rate in. All right? Then we have a couple AP questions. Try these and then look them up. You can also look up, if you hop on YouTube, you can look up, and there are other teachers who do a really great explanation of solving them, and that might help you as well. They may do things slightly different than I did, but it's always good to see multiple ways to do things. Right, so you have 2 of these problems. Both of these are calculator questions. No, 3. We had 3, yeah. 3, 4. Ooh. All right, so there are 4 of these. I would say pick 2. Okay, we don't have to do all of them. If you want to do all 4, that's awesome. You're a rock star. It'll really help you out. These are very common ones, but you can pick 2.